Hi everyone, welcome to this fourth lecture of the course Dynamical Systems, Networks and Applications. So what's the focus of today? So it will be on SIR models, more on networks. And so we will try to fit some COVID-19 data. And so we will discuss one example. It's based on a model which aimed to fit the COVID-19 data in March 2020 in New Jersey and New York states. But well, the topic is more general. So the networks and networks of dynamical systems are widely used to model the dynamics of the spread of viruses and things like that. So we will focus on an example, but of course, the idea is much more general. And before to get into this example, we'll discuss the SIR simple model. All right, so let's go. So just a little bit of context around this course. So most of the models that we discuss are more in neuroscience, which is something that we do at Le Havre University in the applied math laboratory. And I recall that what we do, for example, the brain, the main idea is that you have neurons or assembly of neurons. So those are dynamical systems, and you can connect them and make them interact. So you have a network of dynamical systems. So this is the core idea of these lectures, right? So I discussed in the first lecture, I discussed an example where we discussed a model which aimed to describe dynamics in the cortex V1, visual cortex V1. And that was that you add some neurons. The neurons receive some information from outside. This was modeled by some stochastic drive, and then they interact between them. And according to with a network topology, and then from that results the global dynamic of the network of neurons. All right. But of course, these complex systems, which for us is it's networks of dynamical systems, can be applied also and are applied to the modeling of the propagation of diseases. So a few years ago, I don't know, maybe you were too young, in the island La Réunion, which is a French island, and yeah, which is situated just here, very close to the eastern coast of Africa here. So in the south of Africa, there was an outbreak of disease called the chikungunya, which propagates due to mosquito. All right, and why I'm talking with you about that, in the University of Le Havre, we have some colleagues. I have some colleagues that work on that, and actually a guy is from La Réunion, So yeah, so they had some data, and they built. There was a PhD thesis on that, and yeah, so they built a model to describe the chikungunya disease, and so they wrote a couple of papers on that. And well, I just arrived to Le Havre at this time, but I attended some lectures on that. It was interesting, very interesting. And but mathematically, it's the same. You have some nodes, for example, some small cities, and then are compartments, and they interact, and so with dynamics, and you describe the disease like that. Also, we had some work on the dengue. There was a collaboration with some team in India. I say hi to them if they listen to that, in the IIT Roorkee. And so also there is a lot of so the dengue is a problem in India. So our colleagues there knew quite well, the problematics of the disease, and so yeah, they together with a team at Le Havre, we built a small model, and okay, it was an interesting work on the disease dengue. So I'm talking about that because why? Because to be clear, the epidemiology is not my first domain of application. So I worked a little bit on that. That's why I'm presenting here this lecture. But my main domain of applications is still neuroscience. But at Le Havre, we have some expertise, and I have some colleagues. We did a lot of work on epidemics. It's just the context. And then, so, well, last year, you know the story. There was the COVID, right? So also, we have some connections at Le Havre with the Current Institute at New York City. And so we had a look at the evolution of the COVID-19 last year, right? And so here I gave some people here, some students asked me about the Hudson School of Mathematics. So look, I'm talking to you students, right? This is New York. I apologize. So there's a lot of people going every day from New Jersey to New York in the morning, and going back from New York to New Jersey in the evening. The other direction exists also, but New York is attracting more people from New Jersey than New Jersey is attracting from New York for work, right? And so we're going to talk about the epidemics, the dynamics of the COVID-19. So at the beginning, before the policies on lockdown were effective, there was this movement of people. So yes, this is the geography. This is New York City, Manhattan. This is New Jersey, and you have the Hudson River that makes the separation between the state of New Jersey and the state of New York. So I will talk about later on that. So we were looking at data during the pandemic in March 2019, and of course you cannot get rid of that just you want to see the news were on that. So this is the current governor of New York. And every day, as in everywhere elsewhere in the world, there was a lot of data on the COVID-19. So as mathematicians, yeah, we just look at the data and we try to write something. And so the very basic, it's not so basic, but it is the most used model is the SIR model. So now I'm going to talk about that. So this was a short introduction and a short context. And now this is the outline. So first, I will discuss the simplest SIR model, which is autonomous, and then I will introduce the non-autonomous one, and I will say why it is relevant to take a non-autonomous model. Okay, now then I will use this non-autonomous model to fit the data which was available in last year from New York. Yeah, so it was in 2020, sorry. So in March 2020. And then, well, so, you know, in the United States, I'm talking to French, so maybe US American people, well, know this very much better than me, but often you have New Jersey, New York, and Connecticut, they work together, and they call it the tri-state. And yes, New York and New Jersey, so they are two different states, but yeah, there's a lot of people going from New Jersey and New York, and to New York, from New York to New Jersey. Okay, and then, yeah, so I will say what we can do. I will discuss what we can do after that. This will be your homework if you want to get a grade on this topic. All right? Any questions so far? So far, so good?
No, it's okay.
It's okay? Right, perfect.
Yes.
So let's go on. So let's discuss the SIR model. All right. So this model goes back to Kermack, McKendrick, 1927. I just make a commentary on that. There was a very nice lecture from our friend Jacques de Mongeau on an historical perspective on models for COVID-19 and on some current research. So yeah, Jacques de Mongeau is a doctor, he's a physician, and yeah, he gave a very nice lecture. It's in French. You can find it in the YouTube channel of the Société Française de Biologie Théorique, French Society of Theoretical Biology, and you can find his lecture there. And if you're interested, and if you can understand French, it's very interesting. Okay, so and you will get a lot of information on this model. So here I just start with this model, which is a very nice model and an interesting, nice model. So what is that about? You have susceptible people. They are people which can get the disease. For example, oh, it's all of us, right? It's all of us. We some of us which did not catch, for example, COVID-19 yet, but if we get in contact with some people who are bearing the virus, if we are in contact with them, we can get it, right? So this is before vaccine and everything, all right? So people who are, there are three compartments, right? The susceptible, infected, and recovered. So people who are in the compartment of susceptible can become infected. And so what we observe is that there is a rate at which, when the virus starts, there is a rate at which people who are healthy, who are susceptible, become infected. And this is the more susceptible and the more high, the more infected you will get, right? And you can add, a coefficient. So there is a coefficient, right? So people move from the compartment of susceptible to the compartment of infected with a rate of K and times SI, right? So so this, right? Yeah, you can write that the S at times T plus H equals S of T minus the number of people who are in S times the number of people who are in I times a coefficient K. And of course, you have the time, right? Because time is important, right? And okay, you can neglect that. And that's the idea, right? And after people goes from infected to recovered with this rate. So we can do an analogy, but this is the idea of this modeling. All right, so it's the main idea of this model is really fluxes. So here, let's imagine that this is the number of I. It's like water, okay? So you have infected coming in the I compartment at a given rate, and you have people going out. So in this case, they're becoming recovered at another rate. So the question is that the rate at which people are coming in is greater than the rate at which people are getting out, right? So if the rate at which people are getting infected is greater than the rate at which they recover, then you have an increase of the I compartment. But if now the rate at which people getting infected is smaller than the rate at which they're getting out, they're recovering, then you decrease. And you know, that's give the waves. If you've seen the TV, they're starting, there's the first wave, the second wave, so on and so forth. Well, that's it. That's the main idea of the wave. All right. Let's do some math. So this is an exercise for you. Okay, I spoke about the wave and rates. Okay, I'm reading this theorem, and the exercise for you, it's your personal work of today is to prove that. All right. Okay, so we have then this dynamical system. This is the SIR model introduced by Karen McKendrick. And there is also, I mentioned this reference is the book of Murray, Mathematical Biology. You have also a paragraph on this model. Okay, so let's go back to the theorem. So you start with an initial condition. So this system is, everything is very regular. So the Cauchy theorem gives you a local existence. Well, so once you have local existence, you can prove that actually the solutions are defined for all time, for all positive time. So if you start with S0, I0, R0, positive numbers, then for all t, they all remain positive. For all t, you will have that S of t greater than 0, I of t greater than 0, R of t greater than 0. Okay? You can prove that. And they will never become greater than S of 0 plus I of 0 plus R of 0. Okay, so that gives you the existence for all time and more, a bound, right? The trajectories are bounded. S of t, I of t, R of t with this model are bounded. Okay, you will have to prove that. Then S of t plus I of t plus R of t is a constant. It remains the same. So S of t plus I of t plus R of t is equal for all t to S of 0 plus I of 0 plus R of 0. You must also prove that. All right? Then there exists two positive constants, S star and R star, such that, well, S of t converges to S star as t goes to infinity. I of t, it goes to 0. And RT goes to an R star. All right, you have also to prove that. And furthermore, this S star and this R star satisfies the following equations. S star minus R over K log of S star equals, so this is my final, this is the asymptotic state of the model, right? And this is equal to, this only depends on my initial conditions, I0 plus S0 minus R over K log of S0. And R star is equal to that. And so you have to prove that. Finally, S of t is decreasing, R of t is increasing. All right, and I of t depends. So S of t will always decrease. R of t will always increase. But for I of t, it depends. It depends on what? It depends if the initial condition S0 is less than R over K, then I of t will decrease. But if S0, so in this case, you don't have wave, you know, the wave from the media. In this case, you don't have wave. But if S0 is greater than R over K, then it exists the T0 such that I of t is increasing on the interval 0, T0, and then decreasing on T0 plus infinity. All right? All right. So your work of the day is to prove that. Okay, this is part of the course. So as in the previous lecture, you have to work on that, and then I will give you the solution, right? Any questions so far? No? All right. You're here?
En fait, monsieur, moi, je ne comprends pas pourquoi vous dites que I est décroissant tant que S0 est plus grand que R sur K.
No, that's not what I said. Okay, I will say it in English, then I can say it in French one time. This is not what I said. I said that
Okay.
if S0 is 0, it's the initial condition. So S at time 0. If it is less than R over K are parameters which are given in this model, right? If S0 is less than R over K, then, so this is all well, this is defined at the beginning. This does not change, right? It's fixed. Then I of t is decreasing for all time. Is that clear, or do you need to I say it in French? Mr. Mamadou or Mr. Kasse, is that clear, or
Oui.
is that it's clear?
No, no.
You want it in French? Okay, so
Please.
I'm trying in French for French people, right? S0, c'est la condition initiale, donc c'est fixé. Maintenant, R et K, c'est aussi fixé. OK? Maintenant, si S0 est plus petit que R sur K, ça c'est au début, eh bien I de T, ça va être décroissant. Pour tout temps. Voilà, c'est tout. Ça dépend de la condition initiale. Ça dépend de vos S0. C'est clair?
Oui, je vois, oui.
All right. All right. Okay, and now if my initial condition S0 is greater than R of K, at the beginning I of t will increase, and at some point it will decrease. All right? Okay, work on that. It's interesting to work on that. It's quite simple, and you have just to get into it, and it's quite simple. You can prove that. It's yeah, it's interesting, and this gives you the wave. This is the wave. It occurs in reality. This gives you the wave of the epidemics in general.
Mais monsieur, pourquoi S0? Pourquoi pas S?
S0 is my initial condition. So S, I wrote here S, but it should be S of t, right? From here, it's S of t, I of t, R of t. Often we don't write the t, but it is S of t. While here, it's a number. It's my initial condition. So when you have these dynamical systems, by the Cauchy's theorem, you got existence and uniqueness if assumptions are verified, but for given initial conditions. So a Cauchy problem must have initial conditions. And here my initial conditions, I call them S0, I0, and R0. All right? So it's the S, but at time 0, it's the system. Okay, we will come back later on that. All right, because I will show you some numerical simulations. All right. Okay, so this is your work of today. All right.
So we are now going to prove this theorem 1. So I recall that we are working with the simple SIR model, which writes S of t equals minus k s I. The derivative of t is k s I minus r times I n. Well, I could stop here, right? Here I have a two-dimensional dynamical system, two-dimensional ODE, which has two variables. But well, we add r of t to give meaning to the recovered people, right? So now I want to prove theorem 1, and yeah. So first, let us draw. So I'm drawing here the s-axis and the y-axis here. So this is very regular, so the Cauchy-Lipschitz theorem applies. So I do have existence and uniqueness of the solution for any given initial condition, right? And as we will see, the solution will be defined for all t, y. So yeah. First note that if I take s equals 0, if s equals 0, then I have a solution here which is so 0 and I0 exponential minus RT. Those are all solutions of this two-dimensional system here, right? So which means that if I pick up any solution, if I start with any solution here, I will never cross here this axis, right, by uniqueness of solutions. And also note that if I take I equals 0, then for any s I have a solution, which means that any s0, 0 is a solution, is a stationary point actually. So here, any point here is a solution and is a stationary solution, right? Okay, and that's it. So also here I have a stationary point. And so if I start here, I cannot escape the upper quarter here, okay? Which means that my solutions here, the trajectories s of t, I of t remains here, all right? So if I start with a positive s and a positive I, they remain positive. Now they cannot also escape a region here. They are bounded. Why? Well, we have just to remark that if I take the derivative of s plus I plus r, this is 0, right? And so, yeah, so if I remark here that that r of the derivative of r is always positive, since I remains positive, I have that, so this is 0, so we have that s of t plus r of t plus I of t equals s0 plus I0 plus r0, right? Okay, but this is positive, right? So for any time this is true, but since this is positive, I have that s of t is less than s0 plus I0 plus r0, and the same for I, and the same for r. All right. Okay. So we have some parts of the theorem. I think it's useful here to put the null line here. So if I look here, when do this equals 0? So either I equals 0 or S equals R divided by K. So if, for example, here I choose R divided by K, well, this is a null line. So if I start with an initial condition here, so not that this quantity is negative, and here my Ks minus R, so Ks minus R, if S is greater than R over K, then this quantity is positive. So if I start with a trajectory here, it goes like this, right? And so it is bounded by some quantity, by S0 plus I0 plus R0, so it has to cross this thing, and then it gets here, right? But so now it is well known that such a trajectory, you see, you cannot have a limit cycle here, because S of t is decreasing. S of t is always decreasing. So the only choice is that my trajectory here goes to a fixed point. All right. So you have no choice. If I pick up an initial condition here, the solution must converge to one of these stationary points here. All right. So that gives the result that you have that when t goes to infinity, you have that I of t goes to 0. No choice. You cannot cross this line here, and the stationary points are there, so you need to go here. Okay. And also yeah, so you have that this goes to one of these points. All right. All right. Okay. And then, so now I go back to that. I go back to this equality. So now I take the limit. So I can put S and I on the other side. I take the limit and I get that R of t is converging to S0 plus I0 plus R0 minus S star, right? So, sorry. Now, so I have that R of t equals S0 plus R0 plus I0 minus S of t minus I of t. But this thing is converging, so at the limit I get that R star equals S0 plus R0 plus I0 minus S star. All right, so I have almost proved the theorem. It remains what? It remains to prove that I have some quantity which is constant in this plane. So the quantity is the following one. So I just look at the theorem and I can see that if I look at I of t, I of t plus S of t minus R over K log of S of t. And I'm taking this derivative. All right, I take the derivative. So I take the derivative of this quantity and I just write what is written over there. So I get this is KSI minus minus R times I minus KSI. This is good. Well, you can see that this cancels already, and then minus R over K divided by ST, so minus IS divided by S. All right, I forgot the K here. I forgot the K. So it remains plus Ri. So this is 0. And that's what I wanted. Now this quantity is a constant. So finally, so I will keep. Oh no! I'm going to erase that, and finally I do get that I of t plus S of t minus R over K log of ST equals I0 plus S0 minus R over K S0. And so now I know that this converges to 0 and this is converging to S star, so I get that S star minus R over K log of S star equals I0 plus S0 minus A over K is S0. And okay, I proved the theorem. That's it.
And okay, this is an example, right? This is an example of my I of t for a given model. So I'm going now to show you how to obtain this curve. It's an ODE, but well, I will show you, right? So we will here make a little break. And meanwhile, I will set up the material to show you the numerical simulations. All right, so here is it's a program. This is a program, so it's an ODE, and we're going to use this program to make a simulation of our ODE, SIR ODE. So let's have a short look at it. So my final time is 200. This is a time step, which is 0.001. Okay. Those are important parameters. This is my K, all right? So K bar is my K. My K bar 2 is my R in the model. And K bar 3, well, it's the rate at which people die, right? Because you have some people which goes from I to recovered, but you have also people which goes from I to death, right? But I'm not using that on this model, but after we will use it. So, okay. So you don't need that. You can just have a look at it, but we don't need that. Okay. Here, I don't need these functions here. Okay, and okay, this is my function. So this is so F1, F2, and F3 are the right hand side of my ODE, of my SIR model. You see here, minus K times S times I, sorry. Minus K times S times I is the right hand side of my ODE, right? And the same for F2 and the same for F3. Okay, this is the class system, and okay, I will print that on the file. So T, this will be my S, this will be my I, this will be my R, this will be my death people, and this is, I'm not going to talk this right now, but after I'm going to talk about that. And okay, this is the RK4 method. And okay, so that's it. Now I'm running some simulations, and maybe I'm going to share. Oh, okay. I'm going to share. I'm going to share now the whole screen. Okay, now you see the entire screen of a laptop from which I will run the simulations. So I just compile this program. Everything's good. And now I run it. So, okay. And now I'm going to see the output. No. So what I want is so I want to show the time evolution of I as a function of the time. So the time is my first column in my file, and my I is the third column. So I just print that. And okay, you have that, right? So now I will just take, 200 is too much because everything is going back to 0. So I just want to stop at, for example, 10 or maybe 15. So I will set up the time between 0 and 15 and do it again. And all right, so you got that. So this is my I of t for the model, and new share. So, but this is, this is for which initial conditions is, so S at time 0 is 1000, I at time 0 is 5, and R is 0, and also the deaths are 0. All right, and the parameters, so it's K bar and K bar and K bar 2 is that. So yeah, so if I look at my K divided by R, so I will find so is 0.1 divided by 4. So 0.1 divided by 4, so is 0.025. And of course, my S0 is much more large than that. My S0 is 5,000. All right. So if you remember what was written in the slide, let's see if this is working or not. I guess this will not work. Let me do this one. So just a small remark, right? I just write it down. We add this condition, right? We add this condition, right? So you will have an epidemic if S0 is greater than it was R over K. Yes. Sorry. So, and now here in my program, my R, I made a mistake. R is sorry, I need to check that. No, it's 0. And K, it is so R over K, it's 8 divided by, so it's 40, right? It's 40, right? But my S0 here, in the computation that I showed, it's 5,000. So yeah, that's true. And then you have the wave. All right. Okay, let's come back here. Okay, of course, if I change these parameters, the dynamics are changing. And okay, so that's it about this model. So I can send you this this program if you want to work a little more on that and get a grade. I can share this program with you. All right, so now I'm getting back to that. All right. So everybody's here? Hello?
Yes,
Okay, thank you. Thank you.
you're welcome.
All right. Okay, so, and this is the wave. Okay, what's next? So, a few things. Now, of course, this is the simplest model, the simplest SIR model, right? This is the basis. So you can do some things. For example, you can add a death rate. Well, yes, that's true. It was not present. It was even not present in the previous system. So, okay, you can add here a death rate. You don't need that to compute the solution of the equation, but it's important, right? Okay, and also you can make a kind of probability, meaning that here this is the proportion of susceptible people among the whole population, right? So this is a number between 0 and 1. So it gives you a kind of probability that an infected people meets susceptible people, right? So yeah. Okay, so this is two changes, two modifications from the previous model. And also now, and for application, it is very important from what I've seen. You can make the parameters depend on time, and that's the reality, because there is several factors which make these coefficients vary. For example, typically governments act, and this has an effect on the spreading coefficient, on the coefficient k. If you do a lockdown, you bring your k to a low level. If you do nothing, your k remains high. All right, and there's others, factors. And okay, the same for R and the same for D, right? You can act on the death rates by several factors, all right? Typically, you can think about, you can add some vaccine and of course, you can think about a model with vaccines. And yeah, this is an interesting idea to change this model and to add to think about how the vaccine will act on the R. You can either add some compartments with vaccinated, but typically you can simplify and saying that the vaccinated people are, in the first approximation, like recovered people. So yeah, so people vaccinated, goes directly from S to R, for example. Yeah, so you can add some in there, but okay, we will see that allowing to make the K, R, and D dependent on time, it's very useful for applications. All right, I already said that. All right, so now we're going from the application that we have considered. Of course, there is you can apply this model to every state, every country, whatever you want. Okay, so I'm explaining these pictures. Okay, here now we are using this model, right? So typically K is depending on time, and D also. Actually, R is a constant. Well, it's a choice, and the point is you have to work. You have to your model has to work. That is the criterion to validate your model, right? So in blue, it's the real data, all right? So the real data. So in blue, it's all the people who are known to get the COVID-19 between March 1st, 2020 and March 31, 2020. Right? So this is the confirmed cases alive. And so we just take the data from the New York Times, but you have another data basis if you want. But you know, it is known, there are some studies that some people had the COVID, but they were not confirmed cases. So they were people that were not taken into account in the statistics, right? So there was an approximation that the number of confirmed cases, real cases, was 10 times the observed 10 times the number of observed cases in statistics. So we took 5 actually in the model, all right? So what we did with the model is non-autonomous model, we fit the data with I plus R from the model times 0.2, because I plus R are meant to be the real infected and the real recovered people at time t, and we divided by 5 to get the confirmed case, to get the cases that were counted on in statistics, right? And so, as you see, the model fits the real data. But to fit the real data, we had to adjust the K, right? So the thing goes like that. You adjust K. So my K now is a piecewise constant function, all right? So for example, I don't remember the exact, but you have one value of K here, then you change your K. Here you see there's a variation, small variation in the growing. So this means that we change the K. And okay. And then this is also the data that we add. This is actually the most real data that we get is the deaf people. When they're dead, they're dead. So of course, not all the, maybe there are some deaths related to COVID that were not taken in account, and so it's not exact, but of course it's the, I think it's the data is quite good for deaths. And okay, we tried also to fit the deaths from the model with the real data. So the point was to fit first this quantity and then to fit the death, right? It's a natural thing because yeah, the K has much more impact on the model than the death rate for numbers, right? All right. And this is the initial condition. So why this number? Why this number? It's the people living in New York State from the organism of from statistics with, in US. So it's the census data, right? So this is the census data, I guess, from 2029. So there was more than 29 million people living in New York State, and you start with, in fact, it's one infected people, but one people in statistic means 5 in real data. For us, it's our guess, it's our assumption, and those are the initial conditions, right? Okay, now this is the first. I1 is the time course of infected people if you don't change with your initial K. But to fit the data, we had to change the K. And so, for example, it means that on March 21, less or more, we want to change the K to fit the data. So in green, it will be the time curve of I if I add a K which is constructed by 2 piecewise constant functions. And the same with I3. But as you can see, to fit the data, you have to lower your K, and the hypothesis is that it's the effect of the lockdown. Okay, and this is my final I of t, or final I of t. And so we worked with the data from March. So the data stops around here. And then it's a prediction. Now it's a prediction here. All right. Yeah, so as I said, acting of K, of course, that's what the governments were doing. They were acting on the K of T. And it changes. You make a lockdown, you lower your K. You open, you release policies, your K, it's physical, your K increases. I'm taking strictly of the K. Of course, governments have to take into account different factors. I'm not doing politics right here. And okay, then, of course, sorry, a critical thing in the pandemic was to regulate the flux of sick people entering in hospitals. So a point was to just make a regular linear regression between the I of T and the data from daily people entering at hospital with the COVID-19. And as you can see, for the data here, you can split your approximations in two. So we approximated the data with two linear regressions between H and I, and this works well for these numbers. In New York, during March. And once you have that, you can make a prediction of the number of people which will enter hospitals with COVID. Is that clear?
Yes.
All right. So now you can extend that with you make a network made of two nodes. One node is for New York data, the second node is for New Jersey, and according to the company of transit, which is the main company transporting people between New Jersey and New York, 400,000 people used to commute daily from New Jersey to New York before the lockdown policies, right? So now you have the first node, 1, 1 represents New York, 2, 2, 2 represents New Jersey, and then for each S, I, and R, you add movement of people. So people are going in the morning from New Jersey, mainly from New Jersey to New York, and coming back at night from New York to New Jersey. So you have people who are susceptible, you are people who are infected, and you have people who are recovered, right? And so our choices of C here was to model that people are mostly going from New Jersey to New York in the morning and going back from New York to New Jersey at the night. And then we also put in effect the lockdown policy. And then we fit the data with this model for both New York and New Jersey. So now this is New Jersey, I guess. Yeah, it's New Jersey because New York, I have already shown that. And then you have the waves of infected people, and you see that the wave in New Jersey follows the one of New York, because New York is was the first. It was the first. It was one of. It was the first hotspot in the U.S., if I remember. And this is the reality. First, you had the first in New York, the wave in New York, and then in New Jersey. All right. Okay, and this is again, this is the number of people living in New York and the number of people living in New Jersey. Yeah, so around 9 millions in New Jersey and 20 millions in New York. And as you see, I start in New Jersey, 0 people. So the hypothesis is that people were first infected in New York, then in New Jersey, which was actually the truth. And okay. So again, I spoke for New York and New Jersey because we were observing that, but of course, there were studies like that all across the globe. What's next? Right, now we have data until now. So you can take the model and fit the data until now. Of course, you can try to prove more theorems and things like that. And of course, you can extend, for example, you can extend this model with Connecticut or whatever. Okay, so thank you. And so these are a few references. There's a much more. Oops, sorry. I need. It's not finished. And sorry. So this is a paper from my colleagues on the chikungunya disease. There is a book of Murray. It's not here, but it's easy to recall. It's a famous book on the. It's called Mathematical Biology. You have fewer editions from Murray. So Mathematical Biology from Murray. It's very well known. And there is a chapter on epidemics, which is interesting to read. I spoke also about the talk of Jacques de Mongeau. It's a video on YouTube that you can watch. Yeah, this is the paper with my colleague Aziz Alaoui, and just this one. This also a friend of us. There is one co-author, which is Guillaume Quentin from Le Havre, and this Christiana Silva, which is a friend of us. And they did a model. It's on Portugal, right? She's a researcher, a professor in Portugal at University of Aveiro, I guess, and with some of your colleagues and also our colleague Guillaume Quentin. They made a network model with the different regions in Portugal, and yeah, they provided a mathematical analysis and some other stuff. Okay, that's it. So again, now, if you want to get a grade on this topic, what I propose to you is first, you have to prove this first theorem that I gave you. It's here, theorem 1. Okay, but this is for everybody. It's the homework of the class. If you want to complete the class, you have to prove that. But if you want to grade, you have to return back this proof to me, and then again, if you want to grade, you have to. I can give you the programs, and you have to run the simulations to take into account the data in New York State from March 1st to now, right? Well, if you want a grade, so just contact me and I will tell you what exactly I want. Okay, so I will stop here. I'm saying thank you, and I'm telling you see you next time for lecture